next thing is to do what we want is to prove monotonicity. So what do? We assume the claim is that if f and g are now in this general non-negative measurable and f is less than g, so then we claim that these integrals are ordered also in this setting, in the real general setting. So we have monotonicity. Why is this true? Think about some function f, let's say f hat, which belongs to df. So then f is simple by definition, and f is bounded by f hat is bounded by f. But because f is less than g, so it follows that f hat is simple and bounded by g as well. That means that f hat actually also belongs to dg. And in briefly, we can state this, that we can say that this collection of functions dominated by f is smaller than the collection of simple functions dominated by g. And using this observation, if you look at this integral again, and remember it was the supremum over df. Now we don't use g, but we use f hat here. We use supremum of f hat. Think about f hat is approximating f. So f hat belongs to the simple functions dominated by f. And then we look at, recall this simple integral here. And now we have a supremum over this set, and this should be the f hat. And we have a bigger set where we are now looking at the supremum. So then when we have a bigger set to take the supremum, we get a bigger value. So we get the bigger value when we take the supremum over a bigger set. The same f hat is there. But if you look at this definition, this notion of supremum, by definition, that's the integral of g. So that's the end of the proof for the monotonicity in the extended setting. Let's recall. This integral here extends the original simple integral, and it has the property that it's monotone. Yep, it is monotone in this very respect. The next thing, what we want to do is linearity. Can we do it in a simple way? No. That's actually harder. The linearity to prove this is a way harder, actually. Why is that the case? Let's go here again. Look at the definition. The definition says supremum of something. Think about plugging here some g1 plus g2 or something of this sort. There's nothing linear in taking the supremum. So that's why kind of, if you look at this definition does not look at all linear. This looks a highly nonlinear definition. We still want to prove that this still is linear, although it doesn't appear so. So that's where kind of the challenge is. That's why Lebesgue became famous by actually making this work.